Okay, this is Chapter 10, REDOX Lesson 6 in Regions Chemistry. Today we will be able to identify and state what's happening in an electrolytic cell, and additionally we will be able to state similarities and differences between voltaic and electrolytic cells. So let's review just a little bit of a voltaic cell. This is actually on page 13 in your notes, but you don't have the top part here. I'm just doing a little bit of a review. Remember that red cat anox, reduction is at the cathode, anode is oxidation, and electrons flow from anode to cathode, A to C. A comes before C in the alphabet. If you're given a reaction, you simply will assign oxidation numbers to everything in the reaction and figure out what's oxidized and reduced. If you're not given a reaction, then you're going to use Table J. And remember that the more reactive element is oxidized. Another thing that we have to remember is that the cathode spontaneously attracts electrons because the cathode has a positive charge. So it spontaneously attracts electrons to it. And this is the positive electrode in a voltaic cell. This is the electrode where red cat reduction occurs. And remember, when we reduce, we gain electrons and we become more negative, which means that the oxidation number is going to decrease. The anode spontaneously loses electrons because it is negatively charged, and we know negatives repel. To the cathode. It is the negative electrode in a voltaic cell, and it is the electrode where oxidation occurs. Remember, oxidation is anox. Anode is oxidation. Therefore, there is a loss of electrons, and the species becomes more positive, or the oxidation number increases. Another thing that you want to remember, and we've said this, is that this is a spontaneous reaction in which chemical energy is converted to electrical energy. Okay, so that's voltaic cells in a nutshell. Let's look at electrolytic cells. Electrolytic cells are cells that use electrical energy. To force a non-spontaneous reaction to occur. This process is also known as electrolysis because we're running electricity through a system. An example of this is an alternator that's in a car, and it keeps the car battery replenished with energy. In an electrolytic cell, the cathode is the electrode where electrons are sent, and it is the negative electrode which is opposite of a voltaic cell. It is the electrode where reduction occurs. The anode is the electrode where electrons are drawn away from. And it is the positive electrode, which is opposite of a voltaic cell. So it is the electrode where oxidation occurs, or anox. There are a couple of different types that we need to be familiar with, and these are not in your notes. The first one is called electroplating. Okay, so this is an example of an electrolytic cell. Notice how there is only one cell, as opposed to a voltaic cell, which has two cells, and there is no salt bridge. Notice that you have a battery source. So here you need a power source to drive a non-spontaneous reaction. So with electroplating, we can take one metal and we can plate it onto another metal. What you have to remember about electroplating, and it's very important, is that the object to be plated is always at the cathode. So you want to add this to your notes somewhere. So in this diagram we have a spoon. It could be a ring. It could be an earring. It could be a necklace. Okay. Here we have a spoon, and we're going to silver plate it. You've heard of silverware, where they take silver and they plate it on top of a stronger metal. So because the object is at this side, we automatically know that that is the cathode. And in an electrolytic cell, the cathode is negative. Electrolytic equals cathode, and electro sounds like electron, so it's negative. So if you can remember in an electrolytic cell that the cathode is negative, that means that the anode has to be positive, and then just know everything is the opposite in a voltaic cell. So I want to plate this spoon with silver. So here's my silver electrode, and what happens once I turn the electricity on, the silver solid is oxidized. This says Ag solid 0 turns into Ag plus 1 ions, aqueous plus 1 electron. So over time this electrode is going to get smaller. Okay, all this is going to go away. It's going to get smaller because silver metal is losing electrons and forming silver ions. Now remember that the electrons are traveling from the anode to the cathode, so this is going to be heavily laden with electrons on it. They only have one, but I'm going to just put electrons all over that. And you have silver ions in solution, so positive is attracted to negative. So over here the silver ions gain an electron, so this says Ag plus aqueous, gains an electron and forms Ag solid. So the silver forms solid on top of the spoon, and the spoon becomes electroplated. Here's another example of just somebody's drawing. Here the object to be plated is a screw, and it's at the cathode, and we're going to silver plate it. So this is opposite. So here the screw is at the cathode, it's being plated, silver's at the anode, electricity's turned on, all these electrons line up on the screw. And the silver again is oxidized, so it's going to be Ag going to Ag plus 1 electron. And you have all these Ag ions in solution, and then they on this side the reduction occurs, so you've got the Ag plus 1 electron forming Ag solid, and the screw gets covered with silver. So this is one example of an electrolytic cell. It's called electroplating, and you have to know that the object to be plated is always at the cathode. Another example is, this is referring to electrolysis. So over here in A, we have the electrolysis of a fused salt. And in B, we have the electrolysis of water. And these, just kind of listen to what's going on here. Remember I told you that group 1, group 2, and group 17 elements cannot be found by themselves out in nature. They're very reactive. So you can't go in your backyard and dig up some potassium or some sodium or some, calcium. You're going to find it fused to a salt. So in this example, we started with NaCl solid, which we then heated and became NaCl liquid. Molten just means liquid. So this is liquid NaCl in here. So it had to be an extremely high temperature. And I have 2 inert electrodes. So these electrodes are usually made of platinum, PT, because they're not reactive. And I've got a battery. So what's going to happen is, as I run electricity through this, the electrons are going to line up on this electrode. And when NaCl is molten, it can separate into its ions, Na plus and Cl minus. So the cathode is the negatively charged electrode, so the positive ions are going to be attracted to it. So you've got Na plus 1 electron forming Na solid going on over here. The chlorine, okay, you have chlorine minus going to Cl2 gas. So this has to be 2Cl minus to balance plus 2 electrons over here. So your anode is oxidation. So this is electrolysis of a fused salt. We can also do the electrolysis of water. And here you have a beaker of water, and there's usually maybe some H2SO3 in here, a weak acid. And again, these are your 2 platinum non-reactive electrodes. We have 2 inverted test tubes, and we turn on the power source, which supplies an electric current. And what's going to happen? Well, your negative electrode over here, so this side is your cathode, and this side is your anode. And you've got O2 gas and H2 gas being produced. Now, notice that the H2 gas is being produced at twice the rate of the O2 gas, and that's because the compound is H2O. So you have H plus forming plus 1 electron forming what's going to be 2 H2 gas. So this is going to be 2H. So this should be 2 electrons. Positive 2 and a negative 2. 0. Over here you've got O minus 2 going to O2. So this is going to be 2O. So this is going to be plus 4 electrons over here for the oxidation of oxygen. So the electroplating is really important. Electrolysis, understanding how it works, that the cathode is always negative and the anode is positive in an electrolytic cell. So positive ions are attracted to the negative electrode where reduction takes place, and negative ions are attracted to the positive electrode where oxidation takes place. There is no salt bridge, and this is a forced chemical reaction. You will always see a power source, which is often a battery hooked up to an electrolytic cell, which drives the forced reaction. Okay. Lastly, we are going to summarize both types of cells. I'm going to turn this into a Venn diagram. So I'm going to do one of these things. Okay. So we're going to label this side Voltaic, and we're going to label this side Electrolytic. So first, some things that they both have in common. One is Leo says Ger. So in both cells, loss of electrons is oxidation, gain of electrons is reduction. Red cat, anox. In both cells, reduction occurs at the cathode, anode is oxidation. And the electron flow is always anode to cathode. So those things are common in both of them. So what do we know about a voltaic cell? We know that it is spontaneous. We know that it's chemical energy converted to electrical energy. We also know that the anode is negative and the cathode is positive. We know that it contains a salt bridge and two half cells, or two cells. Okay, what about an electrolytic cell? Well, it's non-spontaneous. It is electrical energy to chemical energy. It requires a power source to drive or force the reaction. And the anode is positive and the cathode is negative. And lastly, and I've never really seen it come up on the Regents yet, but I wanted to just point out that a fuel cell and you hear a lot more about these days. Fuel cells, which are really galvanic cells or voltaic cells, for which the reactants are continuously supplied. So when you think about a voltaic cell, you've got a spontaneous reaction that produces energy. Well, in a fuel cell, we basically never run out of the reactants. The reactants are always there. So you don't have to write this down, but in this fuel cell, it says hydrogen fuel is channeled through field flow plates to the anode on one side of the fuel cell, while oxidant, meaning oxygen or air, is channeled to the cathode on the other side of the cell. So down here in the middle, you've got your polymer electrolyte membrane, which allows certain things to pass through. Here's your cathode, which is positive because this is a voltaic cell, and your anode, which is negative. So you've got the hydrogen gas being funneled through on this side, and you've got the oxygen being funneled through on this side. So at the anode, a platinum catalyst, remember I told you they're not reactive, causes the hydrogen to split into positive hydrogen ions. So you basically have H2 splitting into 2H+. And negatively charged electrons, so plus 2 electrons. So this is what's happening over here. On this side, the polymer electrolyte membrane, which is the purple thing in the middle, allows only the positively charged ions to pass through it to the cathode. So these positively charged hydrogen ions are going to pass through the polymer electrolyte membrane, and they're going to get to the cathode. The negatively charged electrons travel through the external circuit to the cathode, creating an electrical current. And then at the cathode, the electrons and the positively charged hydrogen combine with oxygen to form water. So water becomes a product out of the cell. And that's basically how a fuel cell works. Again, you won't be tested on fuel cells, but you should know that a fuel cell is a type of voltaic cell. Okay, and that is the end of the unit. Over the weekend, I will try to, even though I'm away, and hopefully maybe I can do it before then, put the review video together. All right, have a great day.